in Unit 5, all the variables we talked about were discrete variables. So like with binomials, our variable was like number of successes. And so you could have 3 successes, you could have 4 successes, but you couldn't have 3.274 successes. Is everybody with me? So the big difference, so Unit 5 focused on discrete variables. Unit 6 is going to focus on continuous variables. Like, for example, right now, if I were to walk across the street and pick a singular blade of grass off of the ground over there, what's the length of that grass is continuous, right? It could be 3.2 inches, it could be 3.23 inches, it could be 3.7 inches, et cetera, et cetera. Is everybody with me on like kind of the big difference contextually? Okay. So, when we have continuous variables, let's go ahead and keep going with that blade of grass. Let's say I have my grass is somewhere between 2 inches and 4 inches long. Every blade of grass out there, one might be here, 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 one might. You guys catch my drift in terms of how long that could be. Okay? If the grass is recently mowed, I would imagine it's fairly flat top, but really, really narrow, right? Whereas, at any given day on the summer, Miss Meister's grass is not recently mowed because she is not good about mowing her grass at all. And in fact, if you look in my yard, it says I have a fence on each side because, 3 monsters that would run away if we didn't have a fence. But that fence puts one side of the yard completely in shade and one is almost always in the sun. Okay, you can see it in the wintertime because on the south side there is snow, and on the north side of the yard, same yard, no snow because, you guys know what I'm talking about here? Okay, so in the summertime, if I'm like walking out my back door looking at my garage, the right side of the grass on the right side is way, way longer than the grass on the left side. And that's historically been the truth. Okay, so it is possible that this could actually describe the length of grass, especially if I have more grass that's in the sun than the grass that's not in the sun. Okay? So if I'm looking at this picture, you guys, one thing I might say is, all right, I'm going to go out and pick a blade of grass. What is the probability that that grass is 4 inches tall? What's the problem with that question? My first one might be, how accurate is my measuring device, right? Like, if it's 3.9 inches tall, we might call that 4. It's close enough, right? And what's the probability it's exactly 4 inches tall all of a sudden becomes a really messy question, because what is exactly 4 inches? Because how good is my ruler? How good is my caliper or whatever it is I'm using? Okay? So in reality, if I want to know what is the probability that my blade of grass is 4 inches tall, I might say, hey, what's the probability it's between? We might look at just kind of like this shaded area, yeah? We might say, what is the probability it's between 3 7/8 and 4 1/8 inches? That's close enough. That's what we're going to call 4 inches. Do you guys kind of catch my drift on this? Okay, and so in reality, if I wanted to find then this, I'm really saying, well, what's the probability 3 7/8? Like, that could be what I'm doing, and really what I'd want to do is take that yellow area over the total area. And by doing that, I'm kind of taking into account that the yellow is a lot bigger than is taller than one section, right? Like, I couldn't just say, oh, that's like this width compared to this one. Like, if I look at the yellow area over the total area, that would give me kind of like the probability I'm in that range of values. Is this feeling decent? Okay. Now, we have, in statistics we have, and this is not a term you guys need to, like, remember, but I'm going to kind of talk through conceptually what's going on here. Okay, so we have this blue curve that's kind of outlining this area here, has a special name. That name is called a density curve. And the biggest idea I need you to understand about a density curve is that underneath a density curve is all of the possible outcomes. So the probability underneath, the total area underneath, is equivalent to the total probability of every outcome. What is the total probability of every outcome? 1. So we kind of like create these equations where the total area that describes my graph is 1. So now finding that yellow area is in and of itself enough. Like that tells me the probability. Okay? So when we use a density curve, which your calculator is pre-programmed with one in particular that we care about quite a bit. Okay? What we do is find the area underneath the curve that's in an interval. So we give the calculator an interval and say what is the area in this interval when this is my density curve. Okay? We are going to talk about 2 types of continuous variables. Okay? Today we're going to focus mostly on uniform variables. Okay? But we will also start some deeper conversations about normal variables, which are also continuous. Okay, so suppose the heights of trees are uniformly distributed between 12 feet and 17 feet. What that means, uniformly, means that 12-foot trees happen about as often as 13-foot trees happen about as often as 14, et cetera, et cetera. Okay, so they all have equal frequencies. So we could say, like, what I know about the total area of this curve right now, it's 1. I know that this distance is 5, right? So what's the height of this box so that the area would equal 1? 1/5. Or if I wanted to, I could call that 0.2. One-fifth is 0.2. And combined, they have to equal 1. So 1/5 times 5 is 1. That's how I knew it was 1/5. Okay? So my question becomes, so let's say I'm randomly selecting a tree. What's the probability that it is less than 14 feet tall? Well, 14 feet would be right about here, yeah? Maybe further, maybe here. So according to the density curve, less than 14 feet would be this section. So the question is, what is this area? That's one way we can think about this question, is what is this area? Well, we can say the base of that area is 2, because it's a rectangle, right? So we can just do base times height. 2 times 0.2 is 0.4. Does this feel okay? If something is uniformly distributed, essentially we could say that the probability of any given range will be the width of my range over the total width. This only applies to uniform, because if they're all equally, like really we could say this was 2/5 of this. That's essentially what's happening, 2/5 being 0.4. All right, so suppose package delivery times are uniformly distributed between 3 p.m. and 4:30 was the probability that a given package is set to arrive after 4:15. Is everybody with me so far? So you guys, are you guys with me that we're essentially saying that this package arrives between 4:14 and 4:30 since it can't arrive after 4:30? Another way we might write this, I want you guys to get into the habit. The saying 4:15 is the least arrival, which is also so it's just saying between. We might write as like less than, two less than signs, statements. Okay? So what is the width of my arrival time? How many minutes is it between? It's 16 minutes between 4:30 and 4:14. How many total minutes is my window?
9.
So to find this probability, I do 16 out of 90. Now, some of you might look at this and say, wait a minute, Miss Meister, this was feel free to check me on this. I guessed on this. Okay. Not guess, I did it from memory. Okay, you guys, how many of you saw this and saw, wait a minute, that's a time period, this is Poisson? Did anybody look at this and say, as soon as you see that 3 o'clock to 4:30, it might make us think it's a Poisson distribution like what we learned about on Friday? In this case, our variable was when, not how many occurrences happen inside that time frame. That's what tells me that this is not a Poisson variable. Okay. All right. You guys try this one.
Do we need to write? Needs to be written down, all of it, or?
Just enough to communicate your thinking to me. This isn't normal, so we don't need to normal distribution. We're not using that distribution. We're just doing it. So you're going to say, how wide is the range we're looking at? So this distance, the difference between these two.
Did you see a crane hit a power line this morning?
I read about it. I didn't see it. I know it shut down I-70, so I'm going to assume it's some of the construction downtown. Okay. All right. So you guys, we're going to shift into what we call the standard normal distribution. We have done a lot of work with normal distributions. We're going to formalize it quite a bit today. Because so far what we've said is I'd be like, oh, if I go one standard deviation on either side of my mean, and that was what percent? 68%. So it went 68, and then 95, and then 99.7. Those are approximations, okay? So, but normal distributions, anything that's normal also follows kind of this continuous variable, okay? So, are you guys with me that within one standard deviation of my mean, if we say 68% of the time that happens, well, probability is also really a percent of the time we can expect something to happen. Okay? So what we have here is a very specific normal distribution called the standard normal. Standard normal means that this is the distribution of z-scores. And we kind of talked about z-scores being like your number of standard deviations from the mean. So the mean of the standard normal is 0 because if something is equal to the mean, it is 0 standard deviations from the mean. Okay? And so far, all the questions I've given you have been represented as like a whole number of standard deviations from the mean in some capacity, like, oh, one standard deviation below and two above or something like that. I have yet to give you a question where that number of standard deviations from the mean hasn't been a whole number. Okay? This is where we're shifting away from that. But to give you guys, so my goal from here on out is a calculator functions only. Guys, this was supposed to be in between -1 and +1. Likewise, this is -2 and +2. Okay, so your calculator can calculate the area in between any two numbers you want on a normal curve. Okay, it needs that range of numbers. So for this first question, we're basically doing the equivalent of finding this green area. Now, we already know the answer. What's the answer going to be? Oh, it's going to be pretty darn close to 0.68. Yes? So, I want to show you how to put this into your calculator. All right. So, if you go into that distribution menu, the same one we've been using, okay? At this point, you will not use normal PDF because we're never finding the probability X is exactly one thing. Just like a blade of grass isn't exactly 4 inches, right? We only pick, it's like kind of what's the probability between these two values. Okay? So you're always going to choose option number 2 or or Thursday we'll learn about option number 3. Okay? So go ahead and choose option number 2 for now where it says normal CDF. Now, hopefully for all of you, your calculator is asking you what is your lower and your upper. When it's asking for the lower and upper, the lower and the upper are your boundaries of shading. Okay, so my lower boundary for this first question will be -1. My upper boundary will be +1. All right, the next thing it has is like a weird symbol. That's your mean, which for right now is going to be 0. The other one is your standard deviation. Okay, that's going to be 1. Okay, are we all on the same page? And what are we expecting our answer to be? It works out to be 0.683. All right, what if I do from -2 to 2? What are we expecting to get? 95%. So I draw the second verse. Hey guys, I got 0.954. Isn't that about what we expected to happen? All right. If I ask you, what is the probability that I am less than 1.45 standard deviations below the mean? Are you guys okay with my picture on this before I show you how to put this in? Okay. Now, you guys, if I go 3 on each side, that's 99.7% of my variable, yes, of my values, of my observations. So are we with me? Are you guys with me that if I go really, really, really far below the mean, it's practically 0?
Yeah.
Okay, so here's what you're going to do. Technically, this end is negative infinity. We're going to do negative a gajillion as our lower. Okay, so I'm going to pick that same thing. And I literally just type 1 and a bunch of zeros. And then what's my upper boundary? Negative 1.45. And I got 0.074.
Is your standard deviation still 1?
Your standard, for now, your standard deviation will always be 1 and your mean will always be 0. Okay, if I look at this one, again, mean is always 0 and standard deviation is 1. What's the probability z is bigger than negative 0.2? Bigger than, I would shade to the right. So now what is my lower boundary? Negative 0.2. My upper boundary is a positive gajillion. Mean is 0, standard deviation is 1. You guys, my answer should be a little bit more than 50%, yes? And I got 0.580 or 579. So this menu on our calculator can help us do whenever it's not quite the same, not quite a whole number of standard deviations, we can still go through and find probabilities. And this is a good stopping place. And we'll start from here on Thursday.
Do you have a test next week?
It might be